So yesterday we were looking at some pretty complicated exponential expressions and doing our best to solve them. And the methodology that I gave you guys was to match the bases and then use our one-to-one property to drop the matching bases, set the exponents equal to each other, and then solve for x. That certainly works. And it certainly works really, really well. But we do actually have several other ways to approach this. So for instance, let's say we were looking at that last example where we do 2 to the x plus 1 is equal to 5 to the 2x minus 1. We are trying to get some kind of information out of the exponent. We actually have a tool in our toolkit, other than just rewriting the bases, that allows us to access what is going on in the exponent. Right, so how could I rewrite this exponential statement in order to kind of isolate what is going on in the exponent? Rewrite it as... Say again? So that's the technique that we looked at yesterday, which is changing the bases, matching the bases using the one-to-one property. We're looking at a different technique now, which is going to be rewriting this rather than as an exponential statement. What kind of statement talks about what's going on with our exponents? The logarithmic statement talks about what's going on with our exponents. A couple of different ways that we could approach this. So just a reminder, if I have b to the power of y is equal to x, how can I rewrite this as a logarithm? What is that going to look like? Log base b of x is equal to y. Very, very good. And so this is going to depend on what we want to be b to the y and what we want to be x. Ultimately, it doesn't matter. We kind of saw that we could work this from either side, and it's not really going to matter. But let's just say for the sake of it, we want to think of 2 as our base and x plus 1 as our y, and then the other side as just the other side. Then we could take this statement and rewrite it as log base 2 of 5 to the 2x minus 1 is equal to x plus 1. Okay, so that's pretty good. And then what could I do with the 2x minus 1 that's in my exponent up there? Say again? Bring it to the front with my power rule. And so this would be 2x minus 1 times log base 2 of 5 is equal to x plus 1, which ultimately is what we got when we changed the bases and then rewrote the expression and dropped the base. This is the equation that we ended up solving for x. But this is another way that we can get there rather than just changing our bases, which again is totally fine. It works. It'll work 100% of the time. We also could take our exponential expression, say, well, I'm really looking for what's going on in the exponent, so let's rewrite this as a logarithm so that I have access to that information. And so rewriting our exponentials as logarithms also lets us kind of solve for what's going on in the exponent. We could have been doing the exact same thing with example 1, writing 5 to the 2x equals 5 to the 1/3 and reformatting that as like log base 5 of 5 to the 1/3 equals 2x, and then solving. You get the exact same thing regardless of how you do it. But this is just kind of an alternate way to go about doing this, is rewriting these expressions as logarithmic expressions. But nothing wrong with what we were doing yesterday. I think some people maybe find it difficult to do that whole, that other identity property. So just giving you another way that we can look at it. Let's actually put that kind of methodology here to practice. Again, if we wanted to do what we were doing yesterday, matching the bases, using the one-to-one property to drop everything, we still can. It will still work. But let's try this whole rewriting things as a logarithm method and see what that gets us. So looking at example 3, both A and B, slightly different from what we've been working with up until now, mostly in that the exponential part of my exponential expression is not isolated. In order to rewrite this as a logarithm or to use those identity properties, we need to isolate that b to the power of y piece of our equation here. So looking at 3a, what is being done to my exponential part of this equation? Being multiplied by 20, and so to isolate the e to the 2x piece, I am going to divide both sides by 20. Very good. I get that 5 is equal to e to the 2x. And from here, we could absolutely rewrite 5 as e to some power. In particular, what is 5 going to be equal to as e to a power? E to the what? E to the ln of 5. Absolutely. And then we could drop the e's and we'd get like 2x is equal to the ln of 5. That works. If you felt really comfortable doing that yesterday, this method still works. You'll still get the exact same thing. But we can also rewrite this expression as a logarithm. What is this going to look like rewritten as a logarithm? Say again. No, that's the first step in the methodology. What you would then do is you would do like e to the ln of 5 equals e to the 2x. Base to a power equals base to a power. What do I get to do here? Drop the bases, set the powers equal, so you would get ln of 5 equals 2x, and x equals ln of 5 over 2. So that's just like the first step. So this would be like the way that we did it yesterday, right? And that's fine, that works, that is the correct answer. That's great, perfect. But how could I reformat 5 is equal to e to the 2x as a logarithm? How could I rewrite this? So log base e of 5 or ln of 5 equals 2x, which is exactly the same thing that we see right here. So we are actually going to get the same answer. Ultimately, we get the same result. And so I get that x here is, in fact, equal to the ln of 5 divided by 2. So either way, totally fine. If we were finding what we were doing yesterday, super breezy, not a problem at all, then that still works. That's great. If you were finding what we were doing yesterday to be like really confusing, no idea what's going on, and this clicks a lot more, then that's also totally fine. There are other ways to solve this as well. Taking the ln of both sides would also work, but I'm trying to give you kind of ways that give you a goal. So for instance, one goal is to use the one-to-one property, so I need to match the bases. That could be one goal. Another goal could be I'm trying to access some kind of information about the exponent. To know more about the exponent, I need to write this as a logarithm. So that would be like our secondary goal, or a second goal that we could set. So rather than giving you like arbitrary do this thing, trying to give you more like this is our aim, here are the tools that we have to do it. But there are tons of different ways. Actually, probably like 3 different ways that we can do this. And these are the 2 that I want to highlight. All right, let's try it with b as well. Again, I need to isolate the exponential piece of this statement. What do I have to do to isolate the exponential bit of this? Subtract 5 and divide by 4. I get that e to the 2x is equal to 7 over 4. And then we could change 7 over 4 to be e to a power, just like what we did yesterday. Or we could rewrite this as a logarithm. How do I rewrite this as a logarithm? Very good. And so I get that x is equal to the ln of 7 over 4, all divided by 2. gets to be a little bit hard to see, but taking this value, whatever it is, it's like 0.56 or something, dividing it by 2. All right, questions here with this kind of slightly newer approach to what we're doing, but really also we could have been doing this the whole time, and really also we could be doing the old thing that we were doing this whole time as well, and you would get the exact same thing. Any questions with these examples? Yeah, Dylan.
So the first number that has the exponents, that's always going to be the base of the log.
So
it's going to be e.
Yes, exactly. So the exponential base becomes the logarithmic base. Yes.
And then the other side of the equation is always what?
It's the input of the logarithm. Yeah, exactly. The result of the exponential expression is the input of the logarithm. Yeah. Yeah, Simran. Whatever you want. If you remember from last year, if you've ever done this before, taking the ln of both sides and then jamming that way, that's totally fine. You can do that. But again, these kind of ways are nice in that it's just a little bit more directional than just do this blind operation and see how you end up. Nothing wrong with that, not slamming that if that's how you've been shown it in the past. I just like these kind of two methods because I think they give us a very clear aim, and it's pretty, if not easy, I think it's logically consistent to see like why we would want to do either of these two methods. But whatever way you prefer, I am not a stickler for this. And I will only take it personally if you don't use one of these two ways. And it will only reflect on your grade. It's not a big deal. All right. So let's take a look here at example 4. Up until here, we have been looking at exponential equations, solving exponential equations. The exact same logic that we used for exponential equations will also apply to logarithmic expressions or equations. So in particular, when we were talking about the one-to-one property, yes, we talked about how b to the x equals b to the y implies that the powers are equal to each other. But in the same way, if log base b of x equals log base b of y, so if the powers are the same, then the results must also be the same, right? Taking a base, raising it to a power, taking that same base, raising it to the same power should give us the exact same output. So just like before, where if we can get it into base to a power equals same base to a power, where we can set the powers equal, here, if we can get log of a base, log base something of something equals log base something of something, we can set those somethings, the inside, those results inside of our logarithm equal to each other. Right, so exactly kind of what we see here. So same logic, kind of just going the opposite direction with our one-to-one property for exponents. But also, if I want to access the information that is inside of a logarithmic expression, how could I rewrite it? Yeah, we could rewrite it as an exponential expression, right? That would give us the result. And you'd get like b to the y equals the thing that we are trying to access, that kind of resultant. And so just like with our exponentials, both of these kind of systems of approach will work perfectly well. Pick your poison. I do not care. You can do whichever way you want. There is another way that is equivalent to taking the ln of both sides here, which is taking both of these and raising them to a power. But I actually think that gets very confusing, and so we're going to bypass that and not worry about it too much. All right, so let's take a look at example 4a here. Looking at log base 2 of 2 plus log base 2 of 3x minus 5 equals 3, solving for x. Now, just like with example 3, where we needed really, really cleanly 1 base to a power equals something in order to kind of do our work, we're going to need something very, very similar for our logarithmic expressions. We really need single logarithmic expression is equal to something so that we can either rewrite it or use that one-to-one property, whatever we need to do. Okay, so looking at my left-hand side, I notice that I don't have that. What could I do to my left-hand side to make it so that I just have a single logarithm of 1 base? Okay, and then what would you do with the 1? Absolutely, we could do that. We could subtract log base 2 of 2, which is just the same thing as 1, over to the other side. That would work perfectly. What else could we do? We could also use the product rule in order to combine these. So either you'll get log base 2 of 3x minus 5 equals 2, or you'll get that log base 2 of 2 times 3x minus 5 equals 3. And ultimately, these are the same equation. They yield the exact same thing. Right? So either product rule or just like simplification and then, going through the motions. Whichever one of these we solve, we're going to get the exact same thing, so it doesn't really matter. I'm going to solve the bottom one just because I think the product rule, for instance, if we looked at like C here, we wouldn't really be able to simplify log of 2. We would need to resort to using the product or the quotient rule, as it may be. So I'm going to do the bottom one here, just so we can see it. This is log base 2 of 6x minus 10. But again, nothing wrong with Bryce's suggestion here. Which is very good. Noticing the log base 2 of 2 as well. Okay, so we reach here. We have a couple of different methods going forward. We have 2 primarily methods going forward here. I could rewrite this as an exponential, or I could try to write log base 2 of something is equal to log base 2 of something on both sides of my equation, and then use my one-to-one property to just set those contents of the logarithms equal to each other. Let's start with what I would say for this one is the harder one. How could I write 3 as log base 2 of something? 3 is the same as log base 2 of what? Log base 2 of 2 to the power of 3, which is 8. Okay, so absolutely we could substitute in 3 here for log base 2 of 8, and then you could drop the log base 2s on both sides. Now, the logs are not canceling. We're not dividing by log base 2 on both sides, and then they equal 1 somehow. That's not what we're doing. We are using the one-to-one property to say that if the logarithms of these things must be equal, then the things themselves must be equal, right? A one-to-one property. We're not dividing. We're not canceling. Not really. So that would work. You'd get 6x minus 10 equals 8. But how else could we do this? How could I rewrite this as, say, an exponential? So 2 to the power of 3 is equal to 6x minus 10, which ultimately is the exact same thing. We either way get that 8 should equal 6x minus 10. Right? We either get that log base 2 of 6x minus 10 equals log base 2 of 8, which gives us that 6x minus 10 equals 8, or rewriting it as an exponential, we get immediately that 6x minus 10 equals 8. And either way is fine. Add 10, divide by 6, I get that x equals 3. Okay. And now we hit a potential pitfall, which Dylan did a really good job of asking about yesterday. And that is the possibility of extraneous solutions. So just a reminder Sometimes when we are working with logarithms, when we're using these properties, and this isn't just logarithms, this is in general, you can find this. Sometimes when we are working with these logarithmic properties, we end up with solutions that look perfectly viable, that end up not being perfectly viable, that don't fit the original bill. So a good example of that would be if I looked at like 2 log base 2 of x is equal to, we'll say 4. All right. I could start this off by dividing by 2 on both sides. That would work. But what else could I do here? How else could I rewrite this kind of expression based on my like properties of logarithms? Yeah, this is like log base 2 of x squared. All right. Is equal to 4. And then how could I rewrite this as an exponential expression? How could I solve for x here? Very good. So 2 to the 4th is equal to x squared, which is equal to 16. And what are the 2 values of x that I get where x squared is equal to 16? When is x squared 16? 4 and -4. Okay. So we got 2 solutions. We're happy. We circle them. We're done. What's the problem? One of them's negative. The fact that it is negative is not inherently a problem. We're okay with plugging in, like if it was like 11 plus x, and I plugged in -4 and I got log of 7. That's okay. Plugging in negative x isn't the issue. The issue is when the inside of my logarithm becomes negative, and do either of these solutions make the inside of my original equation negative? We see, yes, that -4. This is just me telling us that we need to be careful about this particular situation, where sometimes we will get things that look like answers, but actually they're lying to us. They are not answers. They are extraneous solutions. And so 4 is not a solution. It is extraneous. Okay. So nothing was wrong with our solving process. We did everything right. We ticked all the boxes. It was all great. It was all fantastic. But we ran into this issue of we got a solution that actually isn't supposed to be a solution. And so we toss it out. It's not actually a solution. So whenever we're doing this process with our logarithms, we want to be very, very careful, especially if I'm altering any of the stuff inside the logarithm. I want to be very, very careful to make sure what I have found is not an extraneous solution. Sometimes I won't have extraneous solutions, and that's great. Sometimes I will have extraneous solutions, and that sucks. And it just depends. I mean, it doesn't suck. You just throw it away. But that is what it is. So looking at x equals 3, if I plug it back into my original equation, do I run into any issues? So log base 2 of 2, I plug 3 in there. Well, that's not going to change anything. That's just a constant. So we're perfectly happy with that. Log base 2 of 3x minus 5, plug 3 in, and I get positive 4. So is that an issue? No, that seems perfectly fine. Nowhere else really to plug it in. And so we are happy and confident that x equals 3 is in fact going to be a solution. Which feels like we just did a lot of work for nothing, but we will see examples where, actually we'll look at one just now, where we try our best to get a solution, and in fact, they're all just extraneous solutions. Okay, but this worked out for us for now. Questions with our methodology here for 4A, which cut off right here. Yes, Simone. So say again. 2 cubed is equal to. So that was from rewriting things. So 3 is equal to log base 2 of 6x minus 10. If you rewrite that as an exponential, that's where we got that. But also, you could have gotten it by doing log base 2 of 2 cubed is equal to 3 and dropping the log. Either way gives us the exact same equation to work from, and we get the exact same result, which is good. We would like our methods to give us the same result in order for them to be valid methodologies. Either way, you will get 2 cubed is equal to 6x minus 10, and that x is equal to 3. So however you like it, whichever is fine. Okay, so looking at 4D here, we could absolutely take this logarithmic expression and rewrite it as an exponential expression. And we would be doing so much more work than we actually need to, because what do we notice about 4D? Yeah, we can already use our one-to-one property. We don't need to do any finagling on either side. We can just go ahead and say that negative 2x squared minus 7x should equal x minus 2, right? That's by our one-to-one property. You would need to combine the logarithms first, so you need to use quotient rule, and then you could do it with 4C, absolutely. And then you could just drop the logarithms, absolutely. So again, we could write it as an exponential. You'd get the same thing. Nothing wrong with that. But why would you do that? This is primed to just set it up as it is and run it. All right. And now we're solving a quadratic. We know how to solve quadratics, hopefully. And so I'm going to offset from 0. I'm going to do this in a way that makes it so that I've got a positive in front of my x squared term. So this is going to be 2x squared plus 8x minus 2 equals 0, adding 2x squared, adding 7x to both sides. Just to make my numbers easier, I notice that each of these is divisible by 2. So I'm going to go ahead and divide everything by 2 here. X squared plus 4x minus 1 equals 0. Just, again, to make it easier, you could absolutely solve that equation above there, and you could get the exact same thing. What are 2 numbers that multiply to make negative 1 that add to make 4? Is there anything that multiplies to make negative 1 that adds to make 4? Not that's easy, not off the top of my head. And so what tool are we going to have to use? Quadratic formula, which we all have memorized and perfectly down at this point, to the point where if anyone were to ask you 10 years from now, what is the quadratic formula for $1,000, we would all win that $1,000, right? And if the answer to that is no, then we need to go home and write it 50 times. All right, I'm tired of us not knowing this. This is something that you needed to know 3 years ago. We don't have an excuse for not knowing it now. All right, this is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And you could use either of our equations. I'm going to use the bottom one just because the numbers are smaller. So a is 1, b is 4, and c is negative 1. And from that, I get negative 4 plus or minus the square root of 16 minus 4 times 1 times negative 1, all divided by 2 times 1, which ends up working out to be negative 4 plus or minus the square root of 20, all divided by 2. You could simplify that a little bit more, but plugging that into my calculator, I get that this is going to be like negative 4.24 and positive 0.24. These are my solutions here. Awesome. Am I done? No, what do I have to check? see if they are extraneous. We could absolutely take both of those and plug them into negative 2x squared minus 7x, but I actually noticed something that's going to go even faster. What happens when I plug both of these into log base 11 of x minus 2? They're both negative. I get two negative solutions, or not negative solutions. I get two negative inputs in my logarithm. And so neither of these are solutions. They are both extraneous. And in fact, there are no solutions. All right. They're a little bit tricky, but just in the case of logarithms, or not just in the case, there are several other cases where you have to worry about this, but you do need to worry about those extraneous solutions. All right, we'll call it there for today. Tomorrow we're gonna look at some fun word problems, which will be entertaining. Some very interesting cases there, and then really just a couple more things before our final test.